Next, for exponential distribution, what is this? Now, here for exponential distribution, it's very related to Poisson distribution. So remember in Poisson distribution, we talk about you selling lemonade. What is Poisson distribution? It arises from independent customers wanting to buy or queue up at your lemonade store. And so they approach independently and randomly at certain rates. Yeah. So and that gave rise to Poisson distribution. If you start recording the instantaneous per minute arrival rates, and then you plot the histogram of the arrival rates. So just to refresh your memory, okay. So this is the kind of picture that we saw last time, right? And so we say a bunch of customers are arriving and they are trying to enter the shop on the left side to try to buy lemonades, right? So I drew up some arbitrary customers, 2 per minute, 1 per minute, 0 per minute, 3 per minute, and so on. So you can see these recorded instantaneous customer per minute rates. And if I start drawing histogram, I say, how many times did I see 0 per minute? Yeah, 3 times. How many times did I see 1 per minute? 4 times, so a bit higher. How many times do I see 2 per minute? That's 3 times, so it's about the same. And 3 per minute, 1 time, and so on. Yeah. So this is how Poisson distribution arises. And remember, Poisson is discrete. Yeah. And how is exponential distribution related to that? Well, it depends on what you are measuring. In Poisson distribution, we asked, what's the distribution of the instantaneous arrival rates? So that was our question, our measurement. In exponential distribution, we ask, what is the distribution of the inter-arrival times? So for example, this could be 0.3, and this could be 1.4, and this could be 0.9, and you get the idea, 0.1, 0.11, 1.7, something like that, 0.8 minutes. Okay. So instead of asking the instantaneous rates of arrivals entering the shop, we ask, what are the inter-arrival times? In other words, what are the times between consecutive customers? Now, why do we ask that question? Because notice that I'm drawing against the backdrop of the same physical happenings. Yeah, so the same customers who arrive at the same fast and furious pace or leisurely pace, we can obtain different measurements of the same physical phenomena. One is the instantaneous per minute arrival rates. The other one is the customer by customer, consecutive customers inter-arrival time, the time gap until I see the next customer. Yeah, the time gap when I see the first customer until I see the next customer, the consecutive customers. So I keep recording these in minutes, and then I start asking, how many times do I see customers who are between 0 to 1 minute? So you can then again plot a histogram, yeah, and from the histogram, obtain a view of the distribution of these numbers. So instead of asking what is the rate of arrivals, maybe now I call it y. All right. So y will be these orange timing measurements. So y is the inter-arrival times. I measure them in minutes, but you can of course get them in seconds, but no point recording in hours because there'll be a lot of decimal places. So to keep the long story short, because time is typically modeled as a continuous random variable, so it is continuous. But just to make the histogram appear, we'll ask how many times do we observe between 0 to 1. It might be here, all right. From 1 to 2, it might be here. 2 to 3, 3 to 4, 4 to 5, something like that. Yeah. So likely we will end up getting some sort of a staircases that is looking like this. Sometimes with a missing teeth and then bumping up again. In practice, these can happen. But long story short is that if we keep these staircases narrow enough and we accept the possibility of infinite time gap, that means there is a chance that after I see a customer, it will take till infinity before I see the next customer. That in real life is not really viable. But if we allow for that unreasonableness, right, then we say that this this green value follows exponential distribution, all right, with the rate of arrival being the same as the Poisson's case. Because here is the beautiful mathematical fact that they all are talking about the same physical phenomena, right? The customers are arriving at an average arrival rate of 1.5. That is a fact. Whether you are interested in measuring the instantaneous rate of arrival or you're interested in measuring the time interval gap between consecutive customers should not change the physical fact. And that is why we have a Poisson of lambda 1.5. That's the physical fact of the situation. You cannot change it just based on the question you ask. Likewise, if we model or we observe the same arrival of customers by measuring the inter-arrival times, we find that the inter-arrival times will follow exponential distribution, but with the same parameter lambda. All right, the lambda here is the rate of arrival that has the same shared meaning with the Poisson distribution. This is very key to realize or understand why Poisson is related to exponential distribution through this story here. Yeah, and of course we can generalize this story. The customers can be photons from galaxies or video packets from San Francisco to your computer. Doesn't matter. Eh? So exponential distribution and Poisson very related depending on the perspective of measurements you are interested in having. So we not only see that this is the link, we also see that when we ask about the instantaneous rate of arrivals, they are all discrete because we will not record half customer, 1/3 customer. We'll just either push it in the front minute or kind of round the person off to the latter minute. For continuous measurements, we will then be able to plot histograms. All right, so of course we should measure very, very huge number of intervals in order to have very smooth curve. And that is why a perfect exponential distribution is really a imagined kind of scenario. And it is perfectly described by lambda e to the minus lambda x. That will be the height of it. And it's a very simple and beautiful formula that basically sums up everything. It describes this, right? So this is the PDF, which will be given by, in general, lambda times e to the minus lambda x. So when x is 0, this whole term disappears, and we find that the height is going to start at lambda, which is why you see that the height is lambda here. So this lambda is just easily gotten out of substituting x equals to 0 here, and all exponential distributions go from 0 to infinity. So we are quite safe to say all exponential distributions start at a height of lambda. Now, lambda is 1.5 and the height is 1.5. Does that mean probability is now 1.5? No, 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 don't worry, because PDF is the height. It is not the probability. Yeah, okay, so it is okay to break the one barrier so long as all the subsequent areas from here until the right end of the curve is going to add up to 1. Now, expected value is 1 over lambda. This you have to be very, very kind of vigilant here, because remember, lambda has the unit of example 1.5 customers per minute, people per minute. So expected value of x, remember what is x? X is the inter-arrival time, so it has to be a time unit, like minutes or hours, right? So the expected value cannot be lambda. The expected value cannot be customer per minute. That's wrong. So it is 1 over lambda, and in this case, my e of x will be 1 over 1.5. And the unit then is going to be minutes, or minutes per customer, and that's fine because customer is just count. That's okay. All right. Why do I point this out? Because you might find that in different descriptions, namely what I saw has been in Wikipedia, different textbooks will also describe the exponential distribution in its own consistent way, but they may just call lambda a parameter. That means a very generic parameter on its own, isolated world. So if you define lambda as just a parameter, they will write their PDF as 1 over lambda e to the minus 1 over lambda x. Their expected value will be lambda itself, because their lambda means the inter-arrival time. And so the average inter-arrival time is lambda. That's okay. Yeah, it's self-consistent. But what I'm trying to describe here is the whole bigger picture of things, how Poisson distribution, a discrete distribution, can and in fact is related to exponential distribution in this very beautiful way. And that is beautiful when you are consistent about the definition of this parameter called lambda. All right, so let's stick with this notation because I see this very beneficial link between Poisson distribution and exponential distribution. So we'll understand lambda as the average arrival rate, customers per minute. All right, so the parameter can be any units, that's fine, but the e of y or e of x in my example, the expected value of the random variable has to be the same as the measurement units of x itself, because it's the average value. So here in this case, my formula will look like 1 over lambda. And I think it's totally a very trivial price to pay for it. It's not complicated nor unreasonable. Okay. And finally, the variance, I need to turn off the picture. And finally, the variance is very simple. It is the square of the expected value. So it's a square of 1 over lambda. So 1 over lambda squared. Another way to say it is the standard deviation of x is equal to the mean of x. All right, so this is one peculiar property of exponential distribution. The standard deviation of x is the mean of x. Imagine this scenario. Suppose a stock price follows the fluctuation of the stock price follows exponential distribution. What that means is the higher the average stock price, the greater the fluctuations. Can you imagine that? Because standard deviation is how fluctuating it is. So that has got a very interesting feel to it, right? Because the larger the value, the larger the fluctuations. Now you might think this is unreasonable for stock price, and I agree. Sorry about that. And another interesting example, have you noticed that your friends who stay further away from office, the further they stay, the more haphazard timings that they arrive at the office? That means the greater the standard deviation of time taken for them to go from home to office. Yeah, because that seems to be somewhat, true for certain, I don't know, certain office, certain locations. At least, it's not unreasonable to say that. So there are cases when that is the case, that we may also then be inclined to borrow this distribution, this exponential distribution, to mimic the scenarios.